All right, welcome back. This is Mrs. Toms. I'm going to go ahead and begin more of the Algebra 1 review. I'll be starting with problem 13, which is on page 9. Below is the graphical solution to an inequality, and which of the following inequalities has the solution graphed above? Well, first what I notice is that this has an open circle. And if it has an open circle, it means that our inequality should not have an equal to sign, which means I can immediately X out choice C because that would have a closed circle with the equal to sign. So now I need to check choice A and B and see which one would have the solution that is graphed. So if I start with A, to solve this I would divide both sides by -3. The -3's cancel. I get X. 6 divided by -3 is -2. But because I divided by a negative, I'm going to switch the inequality around and it is going to become less than. Well, this does not look like my answer because although it is less than, which is the correct direction, it's -2 and my graph has a +2. So I know A does not work, so hopefully that means the answer is B, but I'm going to double check. If I start with -4x minus 9 is greater than -17, I'll do +9 on both sides. Bring down -4x greater than -17 plus 9 is -8. Divide both sides by -4. The -4's cancel. I get X. -8 divided by -4 is +2. And again, because we're dividing by a negative, the sign switches. So I do have a less than, I do have 2. The less than would have the arrow going to the left. So my answer is B. All right, we're moving on to problem 14. Kendall has $88 in her piggy bank. She loves Young Teen magazine and starts spending $3.75 per week. How much money will she have left after 5 weeks of buying the magazine? Well, she's starting with $88. If she's spending money, that means she's subtracting. Every time she buys, it's $3.75. And if we're buying 5 of them, we'll have to multiply $3.75 times 5. So if you do 88 minus $3.75 times 5, the total amount of money that she will have left after buying those 5 magazines is $69.25. Part B. Kendall needs to make sure that she has at least $25 left in her piggy bank to buy a present for her sister's birthday. Let W represent the number of weeks that she has bought Young Teen magazine. Write an inequality and solve it to determine the number of weeks that Kendall can buy Young Teen magazine and still have enough money left to buy her sister a birthday present. Well, we know we're starting with $88. Again, we know we're subtracting $3.75 every time she buys a magazine. And if it's for W weeks, $3.75 will get multiplied by W. And she knows she needs to have enough money to buy her sister a present, and at least 25. At least is represented by the inequality greater than or equal to, so it'll be greater than or equal to 25. Now if we solve this problem, we'll start by subtracting 88 from both sides. It does need to be subtracting 88. If you try to do plus 88, 88 plus 88 does not cancel. So it should be minus 88, because 88 minus 88 is 0. I'll bring down the -3.75W is greater than or equal to 25 minus 88 is -63. And then we'll divide both sides by -3.75. Okay. We'll get W. We'll get 16.8. And again, because of dividing by the negative, we switch the inequality and it becomes less than or equal to. Now, W is supposed to represent the number of weeks. So we can only talk about whole weeks, 2 weeks, 3 weeks, 10 weeks. So we can't use 16.8. So what is the whole number that is less than 16.8? That would be the whole number 16. So she can buy magazines for 16 weeks. go on to page 11, starting with problem 15. Which of the following expressions is equal to 5 to the 2x power? Well, let's start with A. Let's take the 25 to the x power. First, I'm going to rewrite 25. 25 I know can be written with a base of 5, and 5 squared is equivalent to 25. But I still had this x as an exponent, so I'll put parentheses around the 5 squared and put the x on the outside. Now, one of the properties of exponents that we learned is that when we have a power to a power, we take those powers and multiply them. And if I multiply those two powers, 2 times x is 2x, and this is exactly what we were looking for. So my answer is A. Now, another reason why I would know that B and C are not going to work, I'm trying to get something that has a base of 5. And it is impossible for me to write 10 as a base of 5 or 2 as a base of 5. So that also tells me that those answers would be incorrect. All right, moving on to question 16. Vlad wished to solve the equation 64 to the x equals 16 to the x plus 7. There are many correct ways to solve this. Which of the following is not correct as the first step? So let's check choice A. In choice A, we are rewriting things as bases of 2. So let's try to rewrite 64 and 16 in bases of 2 and see what happens. All right, so 64 to the x equals 16 to the x plus 7. If we write 64 as a base of 2, that means we get 2 to the 6th power. And that still has an exponent of x. 16 written as a base of 2 is 2 to the 4th power. And again, we still have the exponent of x plus 7. Well, it looks like I almost have what I'm supposed to. There's what I have there. And this 6 and x would multiply to be 6x. So this one seems to be correct. But I'm looking for what is not correct, so I need to keep going. All right, part B. Let's try this one. This one we want to write everything in bases of 4. So 64 to the x equals 16 to the x plus 7. 64 can be rewritten as a base of 4. It would be 4 to the 3rd power. And 16 can also be written as a base of 4. It would be 4 squared, and we still have the x plus 7. Well, this is what I have here. This would get multiplied and become 3x, which is again what I have there. So I also see that B is correct. So my guess is that C is going to be the one incorrect, but I should still go through the process and see if that is true. So again, I'm going to start with 64 to the x equals 16 to the x plus 7. And I already see that the right-hand side is what it's supposed to be. So the question is, can I rewrite 64 as a base of 16? And the answer to that is no. 16 to the 1st power is going to be 16, but 16 squared is much higher than what I have. I would have to be able to have 16 to the 4th power as they have it, and 16 to the 4th power, if you actually multiply that out, is quite huge. It does not equal 64. So this one is the one that is incorrect, and that's what I was looking for. If we turn to page 12, we're looking at problem 17. At the beginning of the year, Jared began collecting comic books. He started with 1 comic book. At the end of each month, Jared has 3 times as many comic books as he had the previous month. 8 months later, Sally decides to collect comic books. At the end of each month, she has 9 times more comic books than she had the month before. So Jared always has 3 times as many. So that would help me complete the number of comic books that Jared has in the table. Every single time, we would be multiplying by 3. So if I continue that pattern, 27 times 3 is 81, times 3 again would be 243, times 3 again, 729, times 3 again, 2187, times 3 again, 5561, times 3 again, 19683, and finally times 3 again, 59049. That's a lot of comic books. All right, now we want to do the same thing for Sally. Now, Sally didn't start until 8 months later, which is why we're starting down here with one comic book for Sally. And Sally is going to be collecting them, and she has 9 times. So we're going to multiply by 9 each time. 1 times 9 is 9. If we multiply by 9 again, we get 81. Okay, now after how many months will Sally have 6,561 comic books? Well, what we could just do is just go ahead and keep going on the table and see how long it's going to take. So if we go to month 11, and we multiply by 9 again, we're going to get 729. Still not enough. So let's go another month. If we multiply by 9 again, we are going to get 6,561. So that's the number that we wanted. But it's not going to take Sally 12 months because remember, Sally didn't start until month 8. So let's see how many times she actually had to do it. Well, from here to here is 1 month. Here's the 2nd month. Here's the 3rd month. And finally here is the 4th month. So it took Sally 4 months to have 6,561 comic books. All right, part C. Let M represent the number of months after Jared started collecting comic books. Write an expression for the number of comic books that Jared has after M months. Okay, well, what I notice is that for these numbers that are right here, 3 is 3 to the 1st, 9 is 3 squared, 27 is 3 to the 3rd, and every time this exponent that is with the 3 matches the month number. So Jared's expression would be 3 to the m power. Now Sally has something similar. Her 9 is 9 to the 1st, her 81 is 9 squared, her 729 is 9 to the 3rd, 6561 is 9 to the 4th, but hers do not match. Okay, when her exponent is 1, it was at month 9. When her exponent was 2, we were at month 10. But what I do notice is that there is still a pattern. 9 minus 1 is 8. 10 minus 2 is 8. 11 minus 3 is 8. So if I take the number of months and subtract 8, that gets me to what the exponent is for Sally, and then Sally's base is 9. Now in part E, we want to determine after which month Jared and Sally will have collected the same number of comic books. So I want the answer for C and D to be the same, which means I want them to be equal. So let me set them equal to each other. We solve these problems by trying to find a common base. The common base for 3 and 9 would be 3. So I already have a base of 3 on the left. On the right-hand side, 9 can be rewritten as 3 squared, and I'll still have the exponent of n minus 8. Again, by our rules of exponents, we know we can take the 2 and multiply by the m minus 8. If I do that, the new exponent on the right will be 2m minus 16. Now, once the bases are the same, we learned that if the bases are the same, the exponents must be equal to each other. So we'll say that m equals 2m minus 16. To finish this problem, I can subtract 2m from both sides of my equation. This is 1m, and 1m minus 2m is negative 1m. Bring down the minus 16, and then I can divide both sides by negative 1, and m is 16. So the question was, how many months will Jared and Sally have collected the same number of comic books? It will be after 16 months. is when they will have the same number. All right, let's move on to the next page, 13. We're looking at problem 18. A scientist is studying bacteria growth. At noon, she puts one cell of Granicus bacteria in a dish. After each hour, there are 8 times as many bacteria as there was an hour before. At 4 p.m., she puts one cell of Bevis bacteria in a dish. And after each hour for Bevis, there are 32 times as many bacteria as the hour before. So how many Granicus bacteria will there be at 4 p.m.? Well, what did it say we were starting with? We're starting with one cell. So we are starting with one cell. It's times 8 each time. And when it's times 8, that means it's 8 to the h power. So 1 times 8, it's 4 hours later that we want to know, because if we are starting at noon, from noon until 4 p.m. is 4 hours. So I know I have to multiply by 4 different 8s. So 1 times 8 to the 4th power is 4,096 bacteria. And that is the Granicus bacteria. So how many Bevis bacteria will there be at 6 p.m.? Well, the Bevis bacteria didn't start until 4 p.m. So from 4 p.m. to 6 p.m. is only 2 hours. We are starting again with one cell. We are multiplying by 32 every time. And we're doing that for 2 hours, so I'll get an exponent of 2. And 1 times 32 squared is 1,024 Bevis bacteria. So now we're going to let h represent the number of hours after the scientist put the Granicus bacteria in the dish. What does the expression 8 to the h represent? Okay, well, this is the number of Granicus bacteria. I know it's the Granicus bacteria because that's the one that was getting multiplied by 8 every time. And it's the number of Granicus bacteria after h hours. Because I don't know how many hours it could be. When it was up here and it was 4, I knew that I had 4 there. When it's just h, it's h hours. Okay, part D. What does the expression 32 to the h minus 4 represent? Okay, well, the 32 is the one that went with the Bevis bacteria. So it is the number of Bevis bacteria after h hours. And those h hours are after noon. Because remember, they started a little bit later, so we're going to identify that it's actually afternoon. And then why is it h minus 4? Because it started at 4 o'clock. So it is h minus 4 because it started at 4 p.m. All right, part E, fill in the boxes with the correct exponents. We want to rewrite 8 with a base of 2. The correct exponent would be 2 to the 3rd power. We also want to rewrite 32 as a base of 2, and that would be 2 to the 5th power. Now they want us to solve the equation where these two are equal to each other, and we'll be able to use this information that we had just found in part E. So my first step is to rewrite the 8 and the 32 as the common base, and we already see back at part E that the common base is 2. So I'll have 2 to the 3rd, still with the power of h. I'll have 2 to the 5th, still with the power of h minus 4. I can go ahead and multiply my exponents. So on the left, I'll get 3h. On the right, if I multiply, and don't forget to completely distribute, I'll have 5h minus 20. When the bases are equal, the exponents must be equal. So I can set 3h equal to 5h minus 20. To continue solving, subtract 5h from both sides. 3h minus 5h is negative 2h. The 5h's cancel, and I bring down negative 20. And if I divide by negative 2, I find out that h is 10 hours. Now remember that the 10 hours is defined after noon. So 10 hours after noon would be 10 p.m. So it will be 10 p.m. when they have the same number of bacteria. All right, moving on to the next page, we're looking at problem 19 next. We have several of these same type of problems to solve where we need to make common bases and then set the exponents equal to each other. Problem 19, we already have common bases, so we can set the exponents equal to each other. So x plus 2 equals 7. To finish solving this, we simply subtract 2 from both sides. So x equals 5. Now remember, you can always go back and check this problem by plugging it in. So if you were to take this 5 and plug it back in for the x, we'd have, let me just show I'm checking this here. I'd have 3 to the 5 plus 2 power equals 3 to the 7th. And if you do 5 plus 2, it does turn out to be 7. So x equals 5 is my correct answer. All right, problem B. I see that my right-hand side has a base of 5, and I know that I can also make 25 have a base of 5. So 25, if I rewrite it, will be 5 to the second power. I still have the exponent of x minus 1, and that's equal to 5 to the x minus 3 power. If I multiply these exponents together on the left, distributing to both, I will get 2x plus 2, and that is equal to 5 to the x minus 3. And again, when the bases are equal, the exponents must be equal. All right, I'm running out of room a little bit, so I'm just going to rewrite it up here to finish it up. I will start by subtracting x from both sides. 2x minus x is x. Bring down the plus 2. X minus x is 0. And bring down the negative 3. Subtract 2 from both sides. 2 minus 2 cancels, and I'll have x equals negative 5. All right, problem C. 9 and 27 can both be rewritten as a base of 3. 9 is 3 squared, and I still have x plus 2. 27 is 3 to the third power, and I still have the exponent of x. If I multiply these exponents here, I get 3 to the 2x plus 4. On the right-hand side, if I multiply, I get 3 to the 3x. Now that the bases are equal, we can set the exponents equal to each other. The quickest way to solve this equation would be to subtract 2x from both sides. 2x minus 2x is 0. Bring down the 4. 3x minus 2x is x. So I am done. For some reason, my problem on the board here doesn't have d, so let me go ahead and write that in myself. It's 1/4 to the x power equals 8 to the x minus 3. All right, Well, first of all, I have this fraction for this 1/4, which I don't really want to have to work with. So let me go ahead and change that. I know that if something became a fraction, it was because it had a negative exponent. And since this 4 is to the first power, I'm going to go ahead and change that to be 4 to the negative 1 power. Now what I'm going to do is go ahead and multiply those exponents together, and I have 4 to the negative 1x equals 8 to the negative 3rd power. Oh, and I wrote this wrong.
Glenn, please report for the Logan dot. Glenn, report for the Logan dot. Thank you.
Let me catch this up. This should say x minus 3 is the exponent. I just copied it wrong from the paper. Now what I notice is that 4 and 8 can both be rewritten as a base of 2. So rewriting the 4, that will be 2 squared. And I bring down the negative 1x exponent. 8 can be rewritten as 2 to the 3rd. And I bring down the x minus 3 exponent. And then once again, I can multiply my exponents together. So 2 times negative 1x is negative 2x. Distribute when I multiply over here. And I get 2 to the 3x minus 9. And with the bases being equal, the exponents must be equal. So I'll set that equal up here. Negative 2x equals 3x minus 9. So I'm going to subtract 3x from both sides. Negative 2x minus 3x is negative 5x. 3x minus x is 0. Bring down the negative 9. Divide both sides by negative 5. So a negative divided by a negative is a positive. So I can write the answer as x equals 9/5, or because it is a finite decimal, you can go ahead and divide and have the answer as 1.8. All right, moving on to problem 20 on the next page. I have a graph below that shows the price of pizza with up to 4 toppings. So like I noticed that if we have 0 toppings, it's $10.75, 1 topping is $11.75, 2 toppings is $12.50, 3 toppings is $13, and if we had 4 toppings, the pizza would cost $13.25. I also know that on a graph that what is on the x-axis, or in this case the n-axis, is going to be my independent variable. And what is on the y-axis, or in this case is the p-axis, is my dependent variable. Now for A, where we're going to use the phrase is a function of to describe the situation, what we learned before is that it is the dependent variable is a function of the independent variable. So if my dependent variable is the price of a pizza, I will write the price of a pizza is a function of okay, and it's a function of the independent variable, which is the number of toppings. So the price of a pizza is a function of the number of toppings. Okay, and if you stop and think about it, that makes sense. In order to find out the price of pizza, you have to know the number of toppings first. In B, we want to use function notation to describe the point 2, 1250. Well, 2, 1250 is this point right here. Function notation, we put the x value, which in this case is the n, inside parentheses, so p of 2, equals the y value, or in this case the p value, which is our price, so equals 1250. What is the domain of the function? Well, this is a discrete graph because it is not connected. So when we write the domain of a discrete function, we list the individual values. And the number of toppings that we can have is 0, 1, 2, 3, or 4. So I will list each one of those values independently. 0, 1, 2, 3, and 4. Do these points describe a linear function? Why or why not? Well, to be a linear function, we have to add the same value each time. Okay? When I go from 0 toppings to 1 topping, I'm adding $1. But when I go from 1 to 2 toppings, I'm only adding 75 cents. From 2 toppings to 3 toppings, 50 cents. From 3 to 4 toppings, only 25 cents. So if I'm adding $1 and then 75 and then 50 and then 25, I am not adding a constant rate. So if I'm not adding a constant rate, it is not linear. So do these points describe a linear function? No, it is not increasing at a constant rate. Now, what is the range of the function? Again, because it's discrete, we need to list the individual range values, and the range values this time are the prices. So the prices of our pizza, we had $10.75, we had $11.75, $12.50, $13, and finally $13.25. And I should have said this.
Ed Crandall, Paula, please go to the loading dock and move your cars. Ed and Paula, we need you to move your cars immediately. Thank you.
I should say for part C and part E that when we write the domain and range for discrete functions, we should be going in order from smallest to largest. All right, the last problem that I will be doing with you today is problem number 21. You are playing a carnival game. You now have 50 prize tokens. Each time you win a game, you will get 8 prize tokens. As soon as you get at least 100 prize tokens, you will stop playing. So we're given a function that our total number of tokens is going to be 50, which is what we're starting with, plus 8w, and that's because we're adding 8 each time. So we want to fill in the missing values in the chart below. If we have 0 wins, 50 plus 8 times 0 means we have 50 tokens. If I have 2 wins, I'm starting with that 50. I get 8 twice because I have won twice. So that means I'll have 50 plus 16, which is 66 tokens. Now on the last line here, I'm starting with my total number of tokens. So I'm actually going to use my equation to help me solve that. If I know the total number of tokens, I'm going to replace t with that 82. To solve this, I can subtract 50 from both sides. 82 minus 50 is 32. 50 minus 50 cancels. Bring down the 8w. And then if I divide both sides by 8, w is 4. So it will take 4 wins until we get 82 tokens. Okay. What are the independent and dependent variables? The independent variable is like our x. And our x in this case is w, and w is the number of winning games. So I'll write number of wins. Our dependent variable is how many tokens we will have after we know how many wins. So number of tokens. Okay, we can use the same thing we did in the last problem for writing the statement is a function of. We begin with the dependent variable. The number of tokens is a function of the number of wins. Okay, part D. Are the variables discrete or continuous? Well, you can only win a whole number of times, and you can only have whole numbers of tokens. So it is going to be discrete. So it is discrete. Because you can't have fractions of wins or tokens. Okay, E, what does the statement T of 3 equals 74 mean? Well, the number 3 inside here, if you don't remember what it is, look back up here and it tells you. The number inside the parentheses is W, and W is representing the number of winning games. So our 3 represents that we have, if we have 3 wins, and this is the number of tokens, so 3 wins, you will have 74 tokens. All right, we want to complete the domain. So it is starting out 0, 1, 2. I know I could win at least 3 times. I know I could win at least 4 times. I already know that from up here because winning 4 times gave me 82 tokens. But I have to be careful because it's not going to go on forever because the most that I can get is 100 tokens. As soon as I get at least 100 tokens, I must stop. So let's continue the table a little bit more and see what happens. If I have 5 wins, which means I would add 8 more tokens, I would end up with 90. If I have 6 tokens, I would add 8 more, I'm at 98. Well, if I have 98 tokens, I can still keep playing because I haven't yet reached that maximum of 100. So it's when I play that last game, when I finally play game 7 and win, and add 8 more, and I end up with 106 tokens, that's when I'm going to have to stop. So the most that I can have in wins is 7. So my domain continues 5, 6, but it must stop at 7. Part G, what number would you replace the variable w with in the statement T of w equals 90? Well, we could solve it. So 90 equals 50 plus 8w. I could subtract 50 from both sides. 90 minus 50 is 40. 50 minus 50 cancels. Bring down 8w. Divide both sides by 8. And the number of wins is 5. That is the answer, but if I go back up and look at some of the work that I have done before, I can actually see that right there, that 5 wins is going to give me 90 tokens, and that's exactly what I was talking about. All right, that is the end of my portion of your algebra exam.